Alright, so welcome back. I announced at the end of last lecture that we're now reaching the modern times. So we're at least now reaching the 70s with something which is called feedback shift registers. So typically you'll hear FSR, which means feedback shift registers. And the place where you can see that it's well, kind of oldish design is that this is something which is very good in hardware and not particularly nice in software. And being nice in hardware is typical for, well, designs from the 70s and before. This is typical for older designs. The thing was that crypto was pretty much a secret science, so there was not really any public crypto research until the late 70s. And so the agencies were mostly thinking of crypto as replacement for those rotary machines. Those were hardware things which were single purpose, and so they were building smaller and more electronically powered, but still single purpose devices for encryption. Now FSR is something where you have some bits, so typically all of this is over F2. And this was your state. And so this was something, the length k vector in F2, so you have S0, S1, S2, etc. till sk minus 1. Then you're doing something with these bits, namely you feed them back. That means there's something coming out of these state pieces which feeds into a function. So here's the box. This is your hardware device which is implementing a function on S0, S1, S2 till sk minus 1. And then the output of this function, so you compute this thing, and then it is fed back into your state. Well, there's only space for k elements, so 1 pops out on the left. So this is our output. And this part here is the feedback. So to give you an example of what such a function looks like, let's do one with only 2 or 3 inputs. Let me stick to my script. So assume I have the function of S0 till S3. Which is equal to, we're taking S0, adding S1, which you multiply by S2, plus S3, plus 1. So it means we're actually using, let's assume that there is exactly those 4 inputs. We're using all 4 inputs. Some we're just adding, and some we're multiplying. So what happens is we also need some initialization vector. So f, the feedback function, so I should give it a name. So f is called the feedback function. F and the initial state. Determine the output. So the end of last Thursday I was saying, well, we would like to have something more compact than the one-time pad. And we'll need something where we have like a crank that we can turn. So that's basically the clock here. Every clock cycle we output one extra bit. And then we need to have our secrets. Now in this case, the secret is this function. And part of the secret is also the starting state. So matching it with last week when I introduced stream ciphers, then this part would be the key, and the initial state would be this initialization vector. You have to agree on both. If you don't know one of them as an attacker, say you don't know the initial state, you only know the function, you don't know where in the stream it will start. And okay. Typically, I said the starting state, the initialization vector is set in plain, so then the secret would be not knowing this function. So the usage of this is that you get an output stream, you use this as a one-time pad, you add it to your message as a key stream. So use the output stream to encrypt the message. By XORing. And I will just stick to bits here so we have binary sequences. So then the question is, how long is such a sequence? Well, it just continues, right? There is no natural stopping point. So let me rephrase what I want to say is, how long does it take till it repeats? If you have a purely random sequence, somebody sits there, flips a coin, flips a coin, flips a coin. You don't expect any repetitions. Now this thing here with our state of length 4, if I'm reaching the same state as I had before, it will make the same decision. So once I repeat the state, the whole sequence will repeat. So how long till the sequence repeats? And at this point, with our tools, we don't know how to do this, so let's do an example. So we have here, I'll write the output. Here I'll write the state. And here I'll write f of the state. Now this is highly redundant. So for later example, I'll leave out the output. It's just the leftmost entry here. And I'll skip the state. That's just the rightmost entry of the next state. Okay, so who wants to give me a length 4 state? I'm getting inputs of 4 bits. I want somebody 0, 1. What's on? More?
0, 1.
0.
All right. Good. So now we call the crank. That means we output the leftmost bit. We also compute the function of this. So I'm supposed to take S0, then the product of those two numbers. Now 0 times 1 nicely enough is 0. Add S3, which is 0, so I have still 1. And add 1, which gives me 0. So I have computed 0 as a function of state. And now I shift, this one pops out, 0, 1, 0. This is just copied. And then this last bit here shifts in. Okay, now I'm again supposed to compute S0 is 0. The product of these two guys is still 0, plus 0 is still 0, plus 1. So I compute 1. Then I again update. I output the 0. I left shift by 1, so I'm getting 1, 0, 0. And I put this one in S1. Again, my function is 1 plus the product stays 1 plus this one becomes 0 plus 1 is 1. I output 1. I advance, oops, 0, 0, 1, and 1 here. Now, I said before, this is highly redundant. What you see here is just the pieces of the initial state. So the next one will be this 0, then that 0, and that 0. So the f of the state is delayed by 4, the sequence we'll see here. So that hasn't started yet. And we start with just outputting the state. Okay, next computation, this plus the product of these is still 0, plus 1 is 1, plus constant 1 is 0. We're outputting 0, we have 0, 1, 1, 0. Finally a moment where the middle part multiplies to 1, but then we add 1, so we again getting 0. I hope somebody's following because else I'll make mistakes here. I'll be shifting. So we still haven't reached back where we came from. So this is actually a very nice long sequence. 1 plus 0, still 1 plus 0, still 1 plus 1 is 0. Okay, we're outputting 1, shifting, F1, 0, 0. Now we're computing 1 plus a whole bunch of zeros plus 1 is 0. Left shifting 1, getting the all 0 state. Now the all 0 state, all the parts about S will disappear, so we just get a plus 1 here. And unfortunately this blackboard has space, so shifting over 1 more, so 0, then we're having 3 zeros and a 1, and we're computing the output as this plus this product plus 1 is 0. Left shift. All zeros plus 1 is 1. Left shift. We're almost there. Let's hope that we're getting a 0 now because we can stop writing. Okay, so this plus this product is still 0 plus 1. Plus 0 is 0, and yes, we're having 0, 1, 0, 1, 0. And take note that this is the initial state. So here we have the 1, 0, 1, 0, which is the same as what we had up there. So in this case, this sequence is periodic. That means it completely repeats. From now on, we can just predict what happens by looking at what we did up there. So the output sequence is this long stretch, and then it just repeats. So the output sequence is, in this case, it's starting 1, 0, 1, 0. That was our state, so nothing interesting here. Then 0, 1, 1. And then 4 more ones, 4 more zeros. I put a bar over to indicate this is periodic. So this is periodic. With length, I'll quickly count, this is length 11. But if you go for all binary sequences of length 4, there are, well, 2 choices in each of the 4 positions, so we have 2 to the 4, so we have 16 possibilities. So there are 5 missing ones. Do you quickly see one that's missing?
1, 1, 1, 1.
The all 1 state is not there. This is also like, well, the all 0 state is the first thing I checked, but I ran through that, so let's see what happens with the missing ones. some, well, except 5 length 4 strings are missing. So you can check those separately. Oh, one sequence. So this is 1 plus this part is 0, plus 1 is 1, plus the extra one, the constant, is 0. So the function gives us 0. Then we output the first one. We're shifting by 3, by 1 over that's 3 ones. At this moment, before computing this value, I couldn't have told you how long this is because it's all one sequence. It might just have period 1. If this computes to 1, then we're just shifting 1, 1, 1, 1, 1, 1. So it's not that the state is like the minimum length of how many times it could repeat. But in this case, we computed 0, so now it becomes interesting again. And okay, well, this is just different by 1, so we're getting 1 here. We're outputting 1, 1, 1, 0, 1. Now we're getting 1 plus 1 is 0 plus 1 is 1. Outputting 1 here, 1, 0, 1, 1. Computing is the same, so it's 1. Shifting by 1, 0, 1, 1, 1. Now, we know there can't be more, because we now have written down 5 extras. We've cycled through all 11 over here. Now we cycle through the remaining 5 states, so this must evaluate to 1. Let's double check. So this is 0 plus 1 is 1 plus 1 is 0 plus constant 1 is indeed 1. So then we reach at 1, 1, 1. So back to this one. I've been using some words like period and periodic, which I assume you have seen before, but let me briefly define them. So if you have a sequence, you have the SI, where I usually starts running at 0. This thing is called periodic. And it's called the period R. So what we want is that this thing repeats. So if we look at SI plus R, then that's the same as SI for all I greater than equal to 0. Okay, I've been lazy, I've been stopping after 11, but of course it also repeats after 22, it also repeats after 33. So I would like to have a form of minimality in here. So we call it the period if this repetition holds and R is minimal. So we wouldn't call it period 22 if also it repeats after 11. Now sometimes you have sequences that start and only afterwards enter some periodic part. So you have a little bit of warm state and then it just repeats. We haven't seen this example. We're also not going to run through any of the examples, but I should still say that those things also have a name. This is called a sequence. So it is called ultimately periodic if this holds. So normally we would like to start at I equals 1, but we now allow some initial state, so for I larger than I0. So the example, at period R equals 11 for initial state. I should copy that probably used to use the 1010 and period R equals 5 for the all one state. And I've been briefly commenting on that if you have a state of length k, there will be k possible vectors, so the sum of all periods needs to sum up to 2 to the k. For an FSR with state of length k, there are 2 to the k possible states. So the sum of all periods has to be 2 to the k. Is when I was doing the example and saying, okay, well, we don't call this period 22, we call period 11, I was only using multiples of 11. I mean, obviously, if 11 works, then also 22 works. But actually more is true. If I asked you, hey, could this also be periodic with period 45 or 47 or something which is not divisible by 11? Then probably intuition tells you, no, this can't be. If it repeats after 11, then it won't repeat after 47. You can actually prove this. So let's take a sequence. So let Si, I then 0, be a sequence with period R. And that so instead of R, let's take some random L. So let Si plus L be equal to Si for all I greater than or equal to 0. So the definition of periodic means Si plus R is Si, and now, well, there's some L. Then R divides L. So to prove this, this is the typical thing which, if you study mathematics, you will recognize this thing as something where you're likely doing proof by contradiction. So let's assume it doesn't divide it. So that means if you divide L by R, there is a non-zero remainder, and then you're going to show that the remainder has to be 0. So this is a proof by contradiction. So whenever you see something like this, where you're expected to prove that something divides something else, very likely this will be a proof by contradiction. So assume on the contrary if you take if you take L and you write it as some multiple, say T times R plus R0, so this is the remainder. From when you divide by R, and you would like to have, well, when you divide by R, then your remainder is strictly less than R. And to get a contradiction, we also would assume, well, if R divides not L, does not divide L, then R0 is not 0. So there's some remainder which is between 0 and R. Now, we have that Si plus L is Si, and we have that Si plus R is Si. This is from our assumption. This is the definition of being periodic with period R, and this one is what we have as our assumption in the lemma. So we can write by assumption. So we can write Si plus L as Si, and I'll now use this expression for L. So Si plus L times R, T times R, plus R0. So this one goes into this equality sign. And then I'll use this one here, that whenever I add R, I can just ignore it. So let's assume T is 5. I take Si plus 1 times R, Si plus 2 times R, remove another R until 5 times. I'm just left with Si plus T times R. So that means this whole part here is just I. So I have here Si plus R0. Now both of those work for all i's. Oh, and this one is supposed to be Si, sorry. One more error. That would have been usually more pleasing to put the Si under that. Sorry for that. So we now have this equivalent. That means i.e. Si plus R0 equals Si for all I. We haven't done anything. We haven't changed. Like, we've only used these two definitions, and suddenly we found a smaller period. That means this contradicts, R0 is less than R, but R was a period, and we know the period is minimal. So now we have something which is smaller than R, that was the division with the remainder up here, and it still holds the inequality. So this contradicts the minimality of R, and thus this R0 must be 0. Okay, so if you have something which is periodic, then any larger number after which it repeats is a multiple of your period. If it's ultimately periodic, then you have something about the part where it repeats. So then you will have, if it repeats with, like you have 3 steps to get in, and afterwards it's after 11, it's also after 22 or 44 or whatever. Now when you look at the circuitry, so if you're thinking, okay, how does this f function? I've been kind of nice by saying I take either the inputs linearly or it knows there is one product there, so there's the S1 times S2 in my example. But this could be rather high degree, this could be rather complicated. And also be nice, so far we're just doing binary, now that's typical for hardware. A faster way is to just say we add the state bits. Now that makes it that every entry is either there, like every SI is either in the function or not, and then we just sum over those. And that kind of FSRs is called a linear feedback shift register, and that's the class we're going to look at today and on Tuesday. So linear feedback shift registers. So LFSRs are a bit cheaper to implement. And what's important for us, they're also easier to analyze. Then general feedback shift registers, so then general FSRs. In the other linear feedback shift register, the function f is equal to some, you have some ci and you have the si, where I runs from 0 till k minus 1. All you're doing is you're taking ci in f2. If it's 0, you ignore it. If it's 1, you add it. So the ignoring then becomes, you again have your state, S0, S1, S2, Sk minus 1. You again have the feedback. But now this goes through a box which has C0, and this goes through a box which has C1, and then here you add those. This goes through a box which has C2, and then you add those. Oops. Then you have Ck minus 1. This box, you add it to what you have so far, and then the output comes here. This is the general form because I wanted to introduce the variables, the CIs. You typically leave out the ones where CI is 0, and we just draw a line for CI equals 1. Skip this thing if CI is 0, and then draw a closed line if CI equals 1. So as an example, if we have that our, if we would compute the third state as S0 plus S2, now that means 3 plus n, or n plus 3. This takes Sn, and this takes Sn plus 2. So just running these things through, I will typically just leave out the s at the end. And just write S3 equals S0 plus S2. Now, first of all, we have to identify which are the C's. So we have that the Ci's are in front of it. So this one is C0, and this one is C2, and in the middle, which we don't see because it's 0, is C1. So here we have that the output here. We have that the S0 gets taken, S1 gets ignored, and S2 gets taken. We take S1, S0, we take S2, and then we add those two and feedback. So of course you can write as E-box where there's a 1, a 0, and a 1, but this one is a lot easier to draw. So when you see an exercise saying, hey, draw this LFSR, this is totally fine. There's typically no plus in the first one because this is just a wire. So this is really, like you mentioned, the electricity comes out of here as a 0, and nothing comes out of 1 comes and it's a signal, and the signals here get XORed, and there's no signal from here. Or if you have S3 equals S0 plus S1 plus S2, then that looks, you have the S3 state here. S2. And then in this case, each of them has a wire coming out. Now we always want to have that C0 is 1. If the first one wasn't there, then there's just a delay. If C0 equals 0, then we have a picture where there is no wire coming out of S0. And then something happens up here. That means we're just storing 1 bit here. It just gets delayed by 1 clock cycle. So then the sequence is delayed by 1 cycle. And could use a shorter state. So we will insist on C0 equals 1. I should also, up there I was writing it with SI, I should write that the Sn plus k bit is given as the sum over the Ci I runs from 0 till k minus 1, and then the first entry is as n, and it gets plus I. So this is the function using the plus n notation, and if I now move this over, then I have a 0 on the left, adding this one over here, and I get a sum which is over 1 more element, so I have I equals 0 till k over Ci Sn plus I, using, so with Ck equals 1. Writing it this way has one benefit, namely we can reverse the computation. So this makes clear that we can reverse commutation. It's not so typically used in constructive applications. So if you have an LFSR, use it as a stream cipher, you usually just run it forward on those ends. So you start with your secret function and your secret IV, well, secret state, and the other party does the same, and both of you go forward. But when you attack such a sequence, it's often useful that you can also go backwards. So this is not a nice feature, but it exists, so we can't change it. If you have an LFSR, we have that you have the allzero state, if you're taking only the bits from here and you're adding them up with some coefficients, well, if all you have is zeros, then this stays 0. So the allzero sequence is always a separate sequence of period 1. So this stays in the allzero state. So there is always a sequence of period 1. Now if you take any other sequence, so we take an example, and we have now not the allzero state, but let's take the same 1010, and we input this into the S3 equals S0 plus S1 plus S2, then, well, the output sequence will be 1, 0, 1, 0. The next bit will be, sorry, I should truncate. Hold on, we only have length 3, not length 4, sorry. The next bit will be the sum of those, which is, well, 1 plus 1 is 0. Then it will be the sum of these, so that's 1. It will be the sum of those, which is 0. It will be the sum of those, will be 1. So that's just the sequence 1, 0 of length 2. So here we have an example of a state of length 3 giving a sequence of period 2. If you have the allzero, we have length 1. If you have the all1, you see that? What happens? You're summing up 3 ones. That's always odd parity, so it will stay all ones. All right, do we have anything more interesting? If you have 0, 1, 0, that's a subsequence of this one, so that won't work either. So how about 1, 1, 0? That gives, well, 1, 1, 0, at least something is happening. Then the sum of those 3 digits is 0. We do it here. Sum of those 3 digits is 1. Those 3 digits is 1. Those 3 digits is 0. Those 3 digits is 0. So this one looks like 1, 1, 0, 0, 1, 1, 0, 0. So that means this is the 1, 1, 0, 0 of length 4. So we now have the all0 sequence of length 1. We have the all1 sequence of length 1. We have the 1, 0 sequence giving length 2, so that it counts of 4. And now we have a count of 4 more, so now we have all 8 states that are possible with length 3. So we have the periods of 4, 2, 1, 1. And that's all. That's kind of disappointing, because in the nonlinear case, at least we got an 11. Here, the best you could get is length 4. And we're investing a state of length 3, so it's just barely longer than our state. After the break, we'll look at some better ones and figure out how to analyze those. So starting again at 45.